So I hope this is clear. This example is clear. I hope you are still following me. And let's do one more example for you guys. I have prepared this one for you. It's similar, however, this time we have the elastic energy as well. A 2 kilogram mass block is pushed against by an external agent 20 centimeters against a spring, which spring constant. This is given the stiffness of the spring. Then the system is released from rest and it slides over a horizontal surface 1 meter from the point where it was released. I was compressing it, release it, and then it moves 1 meter in the horizontal until it climbs up an inclined plane 45 degrees tilt, as you see in the figure right there. The coefficient of kinetic friction between the block and the surface is 0.1 during the whole trajectory. What is the maximum height it reaches at the end where it stops its motion up the incline? Again, conservation of energy is going to be very, very useful. Let's go with that one. Solution, I will follow the steps described before. Letter A is letter I. State the initial and final position. So as you might see, the geometry is very important. So let us take right away the problem here. This little turn on the path, just forget about this, kind of smooth for this time. However, the block starts at the beginning. It may reach a point B, which we really don't care for the time being. And it will stop the motion at point Z after having got a height, H, and having traveled a distance D. This is going to be important. The distance D traveled along the incline. This distance D here, actually I will erase a little bit D, and we have an angle theta. So as before, dealing with the geometric relations, we have that the height is given by the hypotenuse sine the angle, the opposite leg. We will use that relation in a minute. State the beginning and the end of the motion. Letter number 2, we just said establish your reference level for the gravitational potential energy. Let's move with this letter 2. State where in the world you will call the gravitational energy equal to be 0. Let us define right there, ladies and gentlemen, for 10 points in my solution, the gravity happens to be 0 at the very beginning of the motion, at the very high initial height. Then state number 3, let's proceed as before. In A, what do we have? Initial velocity is 0. Initial height is 0. Initial compression for the spring, because now we have a spring which is compressed. So that means we have some elastic potential energy at the beginning. And it is given, it says an external agent pushed against the block, against the spring, compressing it 20 centimeters, that is to say 20.2 meters. So that's B. In B, we don't care. And in C, the final point, we have the height. H is going to be, we don't know it. However, it's going to be d sine theta, which is an unknown. Well, actually, okay, let's go step by step. The final velocity is going to be 0 because it comes to rest. The final height, Jz, is going to be the height, is d sine theta, which we don't know. And the final compression of the spring at the very end is going to be 0. We may have as well another spring up there in the incline, but that is not important. And believe me, we are almost done with this problem. We just have to state the law of conservation of energy, which I like to write in this way. The kinetic energy at the beginning plus the addition of all the potential energy at the beginning has to be equal to the kinetic energy at the end, plus the addition of all the potential energies at the end, that is gravity and springs, and the energy lost during the movement, the work due to the work of friction. Going from A to C is going to be 0 kinetic energy. It starts from rest. 0 for the gravitational energy. It is at the beginning, our height is 0. However, for this problem, we have some elastic energy, which already defined it is a half K, small k, the stiffness of the spring, x squared, the compression of the spring, has to be equal to the final kinetic energy at point Z is 0 of the incline. However, it gains some gravity, mgh, and we don't have springs at the end, and the losses of energy. Rewriting that equation, and we have this expression right here. Let me go a little bit faster, maybe. It's gonna be K squared mgh plus Q. What is the meaning of that expression? That the total, the whole elastic energy we had at the beginning will be transformed into gravitational energy, and if we lost some energy in the middle, then that should come from the expression comparing the initial and the final energies we have. And actually, this is it. We can already find the, no, because we don't have the H. We have two nodes. So this is a little bit kind of difficult problem because we don't know this one and we don't know that one. However, we know that the work due to the force of friction, please remember, write it down, is going to be the force of friction times the distance. Keep this as a formula if you want, if you will. The work due to the work of force of friction is that one, and the force of friction is going to be mu. Actually, we will have two terms for that. It's going to be, do we know the final height? No. We know the mu now. So this is going to be, since we have two segments of the motion, we will have Q number 1, let's call it this way, in the horizontal segment, and plus the second term in the when you go up the incline, plus the second term. Let us work this a little bit more. In the first part, we have mu k times the normal one times the distance in the horizontal part, plus mu k times the normal in the incline, plus the second distance. So mu k times the normal in the horizontal part is, as you agree, the weight of the block, times the distance which is given. We also told it moves 1 meter above the horizontal surface, plus mu k, the normal for incline, we already saw, is mg cosine theta, and this is the inclination of the ramp, which is related to the height through this formula we just saw a minute ago, d sine theta. So putting all this together, we will get, as we're about to finish now, is going to be rewriting this equation, the distance traveled. So let us go step by step. I am very sorry. This is the stiffness of the spring, 500, compression 0.2 meters, and that's it. That's the first term. Then 2 times for the mass, 9.81, and the height we don't know. We want to find it out. So let's keep it right there. 81 h. Now this term in the middle, we know it because we know the distance along which the horizontal track had some friction was 0.1 for the coefficient, 2 times 981, plus the distance, it was 1 meter. I'm very sorry about that. And then for this term is 0.8, 2 times 9.81 cosine of theta. And this term here, the distance, is going to be, let us rewrite this one, is going to be, this is h divided sine. So I will put it right here for you guys. It's going to be h divided sine. And since the angle is the same, we will have h divided sine 45, and this cosine theta is going to be again as cosine of 45. So putting all numbers together, don't rush that much, Victor, please. 2 7 squared plus 250, you get 10 joules for the elastic energy. 19.62 H, which we do not know. 0.1 times 2 times 9.81. You get 1.962 plus this other term here. Actually, cosine 45, sine 45 is going to be the same. 0.1 times 2 times 8.81 is going to be the same. 9.86962 H. And solving for H with very carefully, you get 8.038 has to be H divided 19.62 plus 1.962 to get a number 21.58. And please cross fingers for the H divided 8.738 inverse 37.2. Happy face, the height 0.0372 meters. And that's it, we are done, and we got the result given in the. So I hope that example was clear, and see you next time. Bye-bye.